Hey, this is Mr. Farrell here, and today we are going over the equation for specific heat capacity, which I've shortened to the heat equation. Okay, so first in this equation, the reason we use it is when we're looking at a specific material and we want to know how much energy it's going to take to heat that material up, or as that material is cooling down, how much heat is it going to give off as it changes temperature while it cools down. So from this equation, you can learn how much energy you have to put into a material to raise its temperature, or how much energy it will give off as its temperature changes and it lowers. Okay, really important equation, very helpful for understanding some cool physics about material science. Um, so when we look at this equation here, um, we see a couple different variables. So first we're looking at Q. Q is the term we use for heat. So it is energy. It has a unit of joules, but it just measures heat energy, energy that is added to something to raise its temperature, energy that leaves something in order to lower its temperature. All right. So again, it has units of joules, which we represent with a J. All right. M is mass. Mass is the amount of particles that make up an object. Okay. Units of mass are kilograms, kg. All right. Then we have delta T. Now, delta is just a Greek symbol representing change. So the change in temperature, all right, is represented by delta T. And the units for that, we use Kelvin in physics, but you can think of temperature changes as changes in degrees Celsius or degrees Fahrenheit. It's just in order for our units to work out in this equation, we want to be sure to use Kelvin. All right. And then for C sub P, so C little p, this is the specific heat capacity. So this is kind of what gives the equation its name. But the specific heat capacity is the particular quality of a material that can only be measured. You can't really, it's hard to know it without measuring it. So there are actually data tables that have the specific heat capacities, the C values for a bunch of different materials. Brick or plastic or cotton, wool, all types of materials have their own specific heat capacity. All right. And in order for this to work out, it's got units of joule over kilogram times Kelvin. All right. Which, as you can see, Kelvin times kilogram in the bottom. This is Kelvin and kilogram in the numerator in the top. So these two are going to cancel out with these two values and leave you with joules. Okay. But these are the units. That's what the different variables mean. Now let's look a little bit more closely at each variable and see how it affects our value of Q, heat. So we're starting with M, the mass. All right. So mass, if we increase mass, what do you think happens to Q? If we decrease mass, what do you think happens to Q? All right. So we're going to go ahead and take a look at this from a pictorial, a picture representation. Then we're going to look at it more closely with math. So let's say, now you can heat up any object, all right? For the purposes of this, I want to talk about water as something that we heat up or see heating up regularly. So remember, mass is equal to the amount of particles that make up an object. So we're going to take a little cup and fill it with water. All right. So we have a little cup full of water here. And down here, we have a bathtub full of water. All right. Awesome. So Q again is equal to the amount of heat that's needed to raise something's temperature, the amount of heat energy needed to raise something's temperature, or the amount of energy that something gives off as it lowers its temperature. Okay? When you look at these two quantities of water, which one do you think is going to require more energy to raise its temperature? If you say at this body of water, then that is correct. This has more mass. It has more particles in it. So you need a lot more energy to heat up all those particles. Okay? Now let's look at the opposite scenario. If both of these are very hot, which one do you think is going to give off more heat energy? All right. If you say at this one, you are also correct. So because it has more mass and more particles, if both of these start off at 100 degrees Celsius, this is going to cool down a lot faster than this one is. This one's going to give off way more heat energy as it cools down because it has a lot of particles all at 100 degrees Celsius giving off energy. This one only has a few particles at 100 degrees Celsius giving off energy because this one just has more particles, okay? So the way that mass works is the more mass you have, the more heat energy is going to be given off, or the more heat energy you're going to need to raise the temperature, okay? And we can see that if we look at the math behind this as well, okay? So let's imagine we double the mass, okay? So I'm going to rewrite this equation. I'm going to double the mass. So instead of m, I'm going to write 2m times delta T times C sub P. All right. Now, if I actually multiply this entire equation out, I can go ahead and remove the parentheses, and it is 2 mass times delta T times the specific heat capacity. And when I compare this to the equation above, the only difference is that the entire equation now gets multiplied by 2 if my mass is doubled. So when I look here, I also have to multiply my heat energy by 2, all right? Because whatever I do to one side of the equation, multiplying it by 2, I have to do to the other side of the equation. Now, it might be a little easier to see it if I say 2m here, and then I multiply everything up, that equals 2 times m delta T Cp. So if I multiply this side of the equation by 2, I also have to multiply this side of the equation by 2. Okay? So if I double my mass, I will double my heat energy. Now let's look at the same situation, but let's cut our mass in half. So I'm going to say 0.5 m for mass. All right? Now again, I could go ahead and multiply this out, and that'll equal 0.5 times mass times delta T times the specific heat capacity. And that gives me the same equation up top, but multiply it by 0.5. So I have to multiply the other side by 0.5. So if I cut my mass in half, I cut my heat energy in half. If I double my mass, I double my heat energy. So mass is related to heat energy because if we increase the mass of the object, we get more heat energy or require more heat energy. And if we decrease the mass of the object, we give off less heat energy, or we need less heat energy to change our temperature. Okay? Now let's go ahead and look at temperature. All right? How do you think changing temperature affects the heat energy given off by an object? All right? So let's take a look. So for temperature, we're just going to talk in terms of the Celsius degree scale, even though we use Kelvin in the equation, just because we can picture Celsius better in our minds. So Celsius, if we have an object, let's say we still have that same cup of water, all right? And let's say we want to change its temperature from 0 degrees Celsius to 30 degrees Celsius, okay? If we do that, we're going to need some energy, right, to heat it up. But which ones are going to require more energy to heat this water from 0 degrees Celsius to 30 degrees Celsius? Actually, let's say 10 degrees Celsius. All right. Or is it going to require more energy to heat it from 10 degrees Celsius to 100 degrees Celsius? All right. Think about it. It turns out that we need more energy to change the temperature from 10 to 100 degrees Celsius than we do to change it from 10 degrees Celsius to 30 degrees Celsius. Now that might make a lot of sense to you all, but it's important to show you here before I show you in the equation, because this way it makes a lot of sense, right? If you're going to make the temperature of something hotter, you're going to need to put in more energy, okay? Now, it works in reverse too. Let's say we have an object that is at 100 degrees Celsius and it cools down until it's 10 degrees Celsius. That object will give off more heat energy as it cools down than an object that starts at 30 degrees Celsius and cools down to 10 degrees Celsius. So the heat equation doesn't just tell us how much energy we need to raise something's temperature, but it also tells us how much energy an object is going to give off as it cools down, okay? And if an object starts at a higher temperature, it's going to give off more energy as it cools down than if it starts at a lower temperature and cools down, all right? Now let's look at the math behind that, all right? So I'm going to go ahead and do just like I did with my M equation. I'm going to double the change in temperature, okay? So let's say my original change in temperature is from 0 degrees Celsius to 50 degrees Celsius, okay? But I'm going to double that range. Instead of going from 0 to 50 degrees Celsius, I'm going to go from 0 to 100 degrees Celsius. So I'm doubling my temperature change. Now let's see what happens, okay? If I do that and I multiply this equation out, I get 2 times M delta T times the specific heat capacity, all right? So again, I end up multiplying my original equation by 2 if I double the change in temperature, okay? So, and this will happen if you double it, triple it, multiply it times 4. The larger the change in temperature, the more heat energy is going to be given off, or the more heat energy you're going to need to put into an object to change its temperature, all right? Awesome. Now let's look at this last one. This one is hard to quantify, but you can still understand it as we look at examples. So C sub P is the specific heat capacity. Now what that means is we take different materials, let's say a plastic bag. Now a plastic bag is not very robust. It's very thin, right? It's not very supportive. But when we look at its heat holding capacity, it doesn't have a high heat holding capacity either. If you were, and do not do this because you may mess up your dryer, if you were to put a plastic bag in your dryer, it would actually melt the plastic bag because plastic bags don't hold heat well. They have a very low specific heat capacity. And if it has a low specific heat capacity, that means the heat required to change its temperature is also going to be low. So a small CP, a small specific heat value, is going to give you a small heat value, right? Small specific heat, small heat, okay? So the less energy you need to actually warm this bag up because its specific heat capacity is so low. Now, you can put a cotton shirt, though, inside of a dryer and it doesn't melt, right? That's because this holds heat better. So this has a higher specific heat capacity, which means that you're going to need more heat in order to change its temperature. You can heat this up and it still doesn't begin to melt or anything, as where this will, okay? So the higher the specific heat capacity, the more energy you need to change the temperature of this object, all right? Now, even among shirts, right? Shirts are made of different materials. So this one is made of cotton, all right? But this shirt, as you can possibly tell through some of the holes, is a little bit more breathable, all right? You can even see through it a little bit. Now, that's because these shirts are made of different materials. This shirt says that it's very good for exercise because it actually will cool you down a lot more because it's more breathable, okay? So this one actually has a smaller specific heat capacity than our cotton shirt. Our cotton shirt will keep you warmer. This one will not keep you as warm. It'll actually cool you down, all right? So even among similar materials, there's still a difference in specific heat capacity, which causes you to feel a difference as you're wearing that different type of clothing, all right? And we can see that in the equation as well. Let's go ahead and double the specific heat capacity. We multiply it by 2. Then we notice that we actually multiply this equation out. We get 2 times delta T times Cp, which means we have to multiply our heat energy by 2. So if the specific heat capacity is 2 times as great, it is going to need 2 times as much energy to change its temperature, or it's going to give away 2 times as much energy to change its temperature as it cools down. And we can do that again if we were to cut the specific heat capacity in half, right? Multiply it by 0.5. We end up getting 0.5 times mass times delta T, our change in temperature, times our specific heat capacity, which means we get half of the heat energy, okay? So hopefully this gives you a better understanding of how the equation works, all right? The more mass you have, the more heat it's going to need to warm up. The less mass you have, the less heat it's going to need to warm up, okay? Same with temperature. The greater the temperature difference, the more energy you're going to need to change the temperature. The lower the temperature difference, or the smaller, then you're going to need less energy to do that. And then, depending on the object, the larger the specific heat capacity of the object, the more energy you're going to need to heat it up. If it has a smaller specific heat capacity, you can heat it up very quickly, okay? But it doesn't just work for heating up objects, all right? Not just heating up, but also for cooling down, all right? If I have a lot of mass, a large body of water, it is going to give off more heat energy as it cools down. If I have a small glass of water, hot water, it's going to give off less energy as it cools down, right? The more particles you have, the more energy they can all give off, right, as they cool down. Same for temperature difference. If I'm cooling down from 100 degrees Celsius to 10 degrees Celsius, I'm going to give off more energy, right? Because I'm going through a larger temperature range. But if I cool down from 30 degrees Celsius to 10 degrees Celsius, I'm not going to give off as much energy because it's a smaller temperature range. And then cooling down also for the specific heat capacity. If my specific heat capacity is very small, then I'm going to cool down very quickly. I won't need a lot of energy. I won't give off a lot of energy to cool down. It'll just be very quick. But if I have a very large specific heat capacity, then I'm going to give off a lot of energy for every time I change temperature. Every bit I cool down, I'll be giving off a lot of heat energy. All right. So hopefully this helps you better understand the equation. Next, I'm going to go into some math work for how to alter the equation. All right.